Welcome to chemistry. Hope everybody's having a great day. So what's the matter? Well, nothing's the matter. Today we're going to be discussing matter in more general terms. We've looked at some specifics about elements and these atoms that make up these elements and the subatomic particles that are within these atoms. But now we're going to look at some general terminology for matter. You will be filling in your matter notes, and you'll notice through this presentation there will be things that are highlighted in yellow that you'll fill in. So just a reminder, we've been discussing elements, and we know that elements are made of specific types of particles, and we can know a lot about a substance, and we can figure out information about it, and know all types of things about it just from what it's made of. So matter makes a difference. What we already realize is that we've discussed matter has mass and has volume. So that leads us to a simple little quote for you today. You have mass, you have volume, so you matter. And then how about a joke for today? You can't trust atoms. They make up everything. All right, anyways, let's move right along, you guys. Talking about matter, we're going to be looking at the general terminology that we use for matter so that when we're in the lab or we're talking about chemistry and we're talking about substances, we can discuss it in more detail, and knowing these details about it helps us as humans to use it in a form or fashion that is useful to us. So first, we're going to discuss heterogeneous and homogeneous or homogeneous substances. Heterogeneous substances are non-uniform, contain regions with different properties than other regions. In other words, there's more than one layer. You could think of like oil being on the ocean. If you have a crude oil tanker that's unfortunately released oil into the ocean, that oil does what? Well, it floats on top of the surface. It creates two layers. Why? It's less dense, and therefore you get a heterogeneous substance or heterogeneous mixture. Compare that to homogeneous, means it's uniform throughout, appears to be one thing. For example, if I take salt and put it in water, the salt dissolves, it is uniform throughout, it's homogeneous, like the ocean water that you swim in. Okay, let's watch a quick video so you get a little more idea about that.
Some of your favorite things are heterogeneous mixtures. It may sound like a scientific term, but its real-world application is super simple. A delicious bowl of Lucky Charms and milk, that's a heterogeneous mixture. Ice cubes in a glass of soda, a big bowl of Halloween candy, even pizza, are all heterogeneous mixtures. It just means that their ingredients or components are not uniform. The components have different properties, and a uniform sample can't be taken across the whole mixture. What does that mean? Dip a spoon into a bowl of Lucky Charms, and sometimes, if you're not lucky, you'll get only milk. Sometimes you'll get the crunchy, crispy things. Sometimes you'll get a marshmallow. And sometimes you might get the perfect bite of all three. See what we mean? A uniform taste or sample can't be taken across the whole bowl. A homogeneous mixture is different from a heterogeneous mixture because the composition of the mixture is the same throughout. Air, coffee, soft soap, even steel, these are all homogeneous mixtures. It's all about the degree to which the components are mixed together and the uniformity of the composition. If you can pick out the components of a mixture the way you can pick pepperoni off pizza, then you have a heterogeneous mixture. If you can't see the individual ingredients and you just see one completely uniform substance, think about the most perfectly stirred glass of chocolate milk, the kind with no syrup residue on the inside of the glass. Then you have a homogeneous mixture.
All right, excellent. So you get the big picture, the difference between heterogeneous and homogeneous mixtures. So again, homogeneous is also the term used. Either one of them is fine. So the first one we're going to look at is this idea of a heterogeneous mixture. Everyone say heterogeneous. Thank you. So it's two or more materials not distributed evenly and separated by physical means, like we saw the Lucky Charms example. If I take sand and I put it in water and I stir it up a whole bunch, guess what happens? Nothing except for the sand goes back towards the bottom. Just like if you're at the beach and you're kicking up your feet in the waves, the sand gets a little bit into the water, it looks a little bit brown. Eventually that sand settles back into the bottom, settles back to the bottom. So there's two layers. That is considered a heterogeneous mixture. Another few more simple examples. If we look at a granola bar, if I eat a piece of granola bar here, or if I eat a piece here, or I have a piece over here, all of those will be a little bit different because it's made of more than one layer. Hey, ice water. The ice, the solid pieces of ice themselves, and the liquid water form two layers. This is a heterogeneous mixture. Or another example, look at this salad here. Hey, there's all kinds of different materials in there. If I take a bite from one spot or another, it's going to be different throughout. Again, heterogeneous. All right, besides heterogeneous, the other key term we need to know is homogeneous or homogeneous, and either term again is fine. With a homogeneous mixture, you have two or more materials evenly distributed. You can think of homogeneous mixtures like salt water, as I pointed out earlier, or Kool-Aid that you might make, or gold, like gold earrings or gold necklaces, because they're not made of pure gold. That pure gold's too soft. They use other metals combined together. They heat them up, melt them. They let them solidify again into certain shapes that you might put around your finger as a ring, and those are called alloys. So homogeneous mixtures can be solutions, which means they have an even distribution of matter. They can be separated by physical means. For example, salt water. If I boil salt water, guess what's left behind? The water evaporates into the air, and the salt is left behind. I can separate them. Compare that to our pure substances. Hey, we've already discussed pure substances. Matter with the same composition throughout. For example, elements. Elements have the same composition throughout, whether I find a little bit of oxygen here or somewhere else in the universe, it's the same throughout. Compounds. We could have simple compounds like maybe carbon dioxide. Or maybe, that doesn't look that great. Let's redo that real quick. We have carbon dioxide. Or we can have H2O. These are always compounds that are pure substances because they are combined chemically, always in the same ratio. There's always going to be 2 hydrogens and 1 oxygen for water, for example, no matter where I find it in the universe. So homogeneous substances. A homogeneous or homogeneous mixture or substance would be like, again, placing salt in water. When we place it in the water, if I took a little bit of sample of the water here or here or here, it's going to be the same throughout. It's homogeneous. It's the same throughout. Gold. If you like to own some gold, well, here's some pure gold, which is called 24 karat gold. However, a lot of you might buy gold that is 12 carats, which it's 50% gold. Or you might buy 18 karat gold, which is 75% gold. For example, if you like to buy some white gold, notice that there's a couple substances, gold 75% and either platinum or palladium 25%. Maybe you want to get even a higher percentage of gold and you get 22 karat gold. Well, that'd be like yellow gold here. You can buy it, again, you can buy this 22 karat, 18, 12. However, look at all the different things that make it up. However, if I took a piece from this little gold sample from my ring, it would be 91% gold, 5% silver, 2% copper, and 1.33% zinc. These are the percentages that make up that substance. They are the same throughout. They mix together evenly. It is called a homogeneous mixture. So what's the difference between these pure substances, pure versus mixtures? Well, one thing that we realize that pure substances have the same physical and chemical properties. While on the other hand, mixtures down here, they can have different chemical properties depending on what the mixture is, either homogeneous or homogeneous. So pure substances are always homogeneous. We can separate them into components by chemical properties, while mixtures can either be homogeneous, or heterogeneous, and we can separate them by physical properties. We know that mixtures themselves are all made of these things. So when we mix them together, either they mix evenly, homogeneous, or they separate out a heterogeneous mixture. I think you're getting the point now. So please identify each of these as either a pure substance, homogeneous, or heterogeneous mixture. Please identify each of these as homogeneous, pure substance, or heterogeneous mixture. All right, now we have the states of matter. We've already discussed the states of matter. We know there's solid, liquid, and gas, and there's plasma, which we'll talk about in more detail later. But for our states of matter, these are important. We know solids are things like ice cubes or diamond or an iron bar, while liquids could be like gasoline or water or alcohol or your blood. And gases would be like the air you're breathing or helium in a balloon or the oxygen that keeps you alive currently. This came out a little odd. I'm sorry about that. I'm not sure why when I downloaded on Notability, but that's okay. The key definition here is properties, characteristics used to distinguish between samples of matter. And so to distinguish between matter, we use physical properties and we use chemical properties. So The physical properties we're talking about first could be such things as their appearance. Describe what they look like. They can be observed anytime. We can observe these properties anytime. Color, odor, taste, texture, density, melting point. These are all physical properties of a substance. Compare that to chemical properties of a substance. Chemical properties would be like, does it combust? Can we burn it? Does it decompose over time? These can only be observed during a chemical change. So physical properties describes its appearance. Chemical properties, when it's actually reacting chemically, we can see the difference. Okay, let's look at physical properties in a little more detail. Physical properties can either be extensive, which depends on the amount, or they could be intensive, which does not depend on how much you have. It doesn't matter how much you have. So let's look at examples of those. Examples of extensive properties. Everyone say extensive? I hope you said extensive. Extensive properties would be things like your volume, your mass, your weight, or size. So all of those things could vary. For example, my weight after I ate a bunch of donuts throughout the week, my weight can vary. My mass can vary. My size can change. Those are extensive properties. Compared to an intensive property, hey, it's the same no matter what. It doesn't matter if I have a very small amount of water or if I have a huge amount of water. The density of the water is always going to be 1 gram per milliliter based upon this temperature. That's at room temperature. Melting point. Hey, at what temperature does it melt? Or the boiling point. It doesn't matter if I have a little glass of water or I have a swimming pool of water. It's going to boil at 100 degrees Celsius. These are intensive properties. So here's some more examples. I'm not going to go through each of them. I just want you to have them in your notes so that you can use this as a reference. These are all physical properties. Color, hardness, odor, taste, state of matter, luster, flexibility. Does it conduct heat? Does it conduct electricity? Its shape, ductility, malleability. So ductility means can you make it into wires, and malleability means can I form it into shapes that I want, like the shapes that we see over here of these different pieces of jewelry, or copper that we use, for example, in the plumbing of our homes. Please list some physical properties of this sugar cube you see here. Thank you. Chemical properties. As we described earlier, these can only be observed when the substance is changing into a different substance. There must be a chemical change taking place, and we can observe these chemical properties. Chemical properties, hey, ability to burn, tarnish, rust, decompose, react with other chemicals. All of these are examples of chemical properties. Please list some chemical properties of this wood. All right, so who cares? Why do we need to know these things? Well, by knowing these things, it helps us understand and use parts in a way that's helpful to us. For example, we know that titanium is super strong. That's why we use it for jet engines. We also know that it's rust-proof, and we know that because it's rust-proof, we can use it, and it's non-allergenic, we can use it for artificial joints like we see here. Or a lot of people use it for piercings. All right, moving along. Vanadium, knowing some properties about vanadium, the element vanadium. Hey, we add a little bit to some titanium and it's able to make some really cheap tools, but also very strong tools. So adding a little bit of vanadium to titanium makes really, really strong tools. You know about helium. Not only is it an inert gas, we realize that it's non-reactive, but it's lighter than air, and that's why we fill it up with balloons, like in the movie Up, great movie. Or we know that it can make our voice sound all funny. So helium has various chemical and physical properties that we use to our advantage. Sulfur. I'm hoping we get to use some sulfur later on this year. It does have an awful smell. It does have a rotten egg smell. And onions and garlic, for example, have sulfur in them. If you've ever had a stink bomb go off at school, which we've had a number of times, hey, that is made from a sulfur component. Sulfur is also very flammable, and it's used in gunpowder, for example. So knowing chemical and physical properties of substances helps us understand how to use them. All right, another one, chromium. Hey, if you have a chrome-plated bumper, for example, or jewelry or silverware, these are made with this element, chromium. Again, knowing properties of chromium helps us to make materials that we can put to good use. Please classify each of these as a physical or chemical property. So please classify each of them as a physical or chemical property. Awesome. Thank you guys for doing that. So, big point, we've learned about homogeneous and heterogeneous mixtures. We realize that we can have physical or chemical properties of substances. And more than anything else, I want you to realize that all of this matters. Have a good one.